Chapter 3, Probability Distributions and Probability Densities. In second chapter, we learned about sample space, event, and how to calculate probabilities. Now let's see how to apply probability to random variables. If S is a sample space with a probability measure and X is a real valued function over the elements of S, then X is called a random variable. We usually denote random variables with uppercase letters W, X, Y, Z, and so on. Then the values that can be assigned to the random variable using the corresponding lowercase letter. Let's look at the first example. Think about rolling a balanced six-sided dice. If we denote our random variable X to be the outcome of rolling a balanced six-sided dice, we know that a dice contains 6 sides, so we may end up with one of these 6 sides. So the outcome of this dice, the X, can contain 6 possible values, either 1, 2, 3, 4, 5 or 6. So these are the values that X can contain. Now let's try to write down the probabilities of these X's. Since the dice is a balanced one, all these 6 sides have the same probability of being the outcome. The total probability is 1, therefore the total probability 1 should be equally divided among all these 6 values. Therefore, the probability of each of these sides will end up with 1 over 6. Now you see the random variable X, the values that it can contain, and also their corresponding probabilities. This is called how the total probability is distributed among all possible outcomes of the random variable X. This is called the probability distribution of X. Let's look at the second example. In a sample of 50 households, 10 families has 2 members, 15 families had 3 members, 12 families had 4, 8 had 5, and the rest had 6 members. List the elements in the sample space and corresponding probabilities if the random variable X is the number of members in a family. So you see the random variable X, that is the number of members in a family. So the possible values that X can contain, you see 10 families had 2 members, 15 3, 12 4, 8 5, and the rest had 6 members. So according to this example, X can contain values from 2 up to 6. Altogether there are 50 households. Out of them there are 10 with 2 members. So the probability of X having a certain value, simple X, in this case when simple X is 2, there are 10 out of 50, which is 0.2. There are 15 families having 3 members, so 15 out of 50, which will be 0.3. And there are 12 having 4 members, which is 0.24. And then there are 8 families having 5 members, which is 0.16, and the rest of the families had 6 members. If we add up these numbers, 10 plus 15 plus 12 plus 8 and 5, up to 5 members, we end up with 45 out of 50. So the rest will be 5 members out of 50, which will be 0.1. Now you see the possible outcomes of the random variable x and their corresponding probabilities. If you add these probabilities together, 0.3, 0.2, 0.3, 0.24, 0.16 and 0.1, they will add up to the total probability 1. So this is the probability distribution of the random variable x. Now let's try to define exactly what a probability distribution is. Before we do that, I will recall you how we categorize random variables. If you can remember, random variables can be either numerical or categorical. In this chapter, we are going to consider only the numerical variables. They can be also divided into continuous and discrete. What is the difference between continuous and discrete random variables? In discrete random variables, we only get whole numbers. You cannot have fractions or decimals for a discrete random variable. For example, number of students in a class. The values that x can get will be something like, for example, 45 students in a class, 100 students in a class, 200 students in a class, and so on. You never get 145.75 students in a class. It's not possible. You cannot have fractions. So this is a discrete random variable. On the other hand, when it comes to continuous random variables, they contain all possible values within a given interval. So they can contain any value within a given interval, all the decimal places, fractions and everything. For example, the temperature. If you measure temperature, you can come up with 35.27 degrees Celsius and so on. So you see, you can have decimal values or fractions. These are continuous random variables. Now, depending on the type of your random variable, the way you define probability densities will be different. Therefore, in this chapter, we are going to look at both discrete and continuous type of random variables, the definition, examples and theorems for these two types of random variables separately. So first, let's start with the discrete case. So the second section is the discrete random variables. The variables defined over discrete sample space, that means they can contain only whole numbers. They are known as the discrete random variables. For discrete random variables, let's define the probability distribution function. Let x a random variable, a discrete one, then the function given by px. For each x within the range of the uppercase x is called the probability mass function. This is simply the table we have already prepared in example 3.1 and 3.2. You see the possible values that x can get and also the probabilities of x. So that is called the probability mass function. Theorem 3.1. A function can serve as a probability distribution or PMF for a random variable x if and only if the following two conditions are satisfied. What are these two conditions? Each probability value that you calculate for the values of x, they should be greater than 0. And then when you add up these probabilities, they should add up to 1. Now let's go back to that example 3.2 and check whether these two conditions are satisfied. So we had the random variable x, 2, 3, 4, 5 and 6. And we had the probabilities of x, which were 0.2, 0.3, 0.24, 0.16 and 0.1. Okay, let's check whether the first condition is satisfied. You see the px values, all of them are greater than 0 and they are less than 1, so they are probability values. If you add these values together, you will see that you end up with the total probability 1. Therefore, both conditions are satisfied and we can say this representation of this table is a valid PMF for the random variable x. Okay, so we can say that since both conditions are satisfied, this Px, the table that we see, is a proper PMF. So simply a PMF is for a discrete random variable, if you can figure out all possible values of x and their corresponding probabilities and list it in a table like this, we call it the probability mass function. And those Px's should satisfy the above two conditions. Can we represent this graphically? Okay. Here's our y-axis and the x-axis. X-axis contains the random variable x, the possible values that x can get. So in our case, it starts at 2. And 6. These are the midpoints. And we have the probability Px on our y-axis. Try to draw them in approximate scale. So it will go up to 1. Okay, we don't need all of them. So when x is 2, we get probability up to 0.2. 3 goes up to 0.3. 4.25. 5 is 0.16 and 6. So you can see a simple line representing the probability at each and every point. Because these are discrete, you do not have any probability assigned for values in between these values. Okay, these are the fractions 2.1, 2.2 and so on. So they do not contain any probability. Only the point probability is there for discrete random variables. Exactly at 2, this is the probability. Exactly at 3, here is the probability. Okay, and you cannot have the fractions or decimals. So in between these values, you don't see any probability assigned for them. This is how you draw a PMF for a random variable x. Now let's see how to get the cumulative density function, usually denoted as CDF. If we have a random variable capital X, the cumulative density function, which we denote as capital Fx, it is the probability that the random variable x is less than or equal to x, which means if you add up the probabilities of x all the way up to a certain value assigned for simple x, So we add all the probabilities together. That is called the cumulative density function. How do we find the CDF? This is very easy. What you have to do is add up the probabilities on top of each of the x's, starting from the first value up to all the way to the end. If you use the same example, 3.2, these are the x's. So rather than writing capital X equal x, if you want, you can write simply px. Okay. 2, 3, 4, 5, and 6. These are the px's. Point 1. Our CDF, capital X, fx will be, at the very beginning you have 0.2. When x is 3, you add 0.3 and the value above it. So 0.3 plus 0.2, which will be 0.5. When it comes to x equals 4, you have to add 0.24 to everything above it. So 0.5 plus 0.24 will be 0.74. When x is 5, you have 0.16 plus 0.74, which is 0.90. When x is 6, 0.1 plus 0.9, you end up with the total probability 1. So the probabilities are added one by one till the end. Since this is a proper PDF, at the end you should end up with the total probability 1. So this is called the CDF, or the cumulative densities of the random variable x. Okay, so this is f2, this is f at 3, this is f at 4, f at 5, and f at 6. Okay, if you represent this graphically, similar to the PMF, here's our x, here's capital Fx, can go up to 1, 2, 3, 4, 5, and 6. Everything below 2, it is 0. Probability is 0. It goes up to negative infinity. This goes up to positive infinity. Excuse me. So when x is 2, fx will be 0.2, and it will go likewise. And when x is 3, it will jump up to 0.5. Okay. So 0.5 is obtained at 3, but all the way up to 3, it remains at 0.2. And soon after you enter x equals 3, you get the CDF 0.5. And it will continue up to 4. And at 4, it will attain 0.74. And it will go up to 5. And soon after you attain 5, the probability will be 0.9. And then it will go till the infinity, up to 6. And at 6, it will attain the total probability 1. And it will remain at 1 till the positive infinity. So this is how you represent the CDF in a graphical manner. You can see that this is a step function. Okay, this is a step function. Okay, so the colored dot mentions the exact probability, and the open one not yet attained, but soon after it goes to 3 it jumped up to 0.5. So that is how you represent the step function. Okay, now if you have the probability mass function and the CDF nicely listed, you can easily calculate probabilities at certain corresponding values of x. So in this third example, let's try to find out the PMF, the CDF, and also let's try to calculate probabilities of this random variable. Okay, so we have the function given by Px, which is x plus 2 over 25, and the possible values of the random variable x is 1, 2, 3, 4, and 5. We have to check whether this is a probability mass function of a discrete random variable, and then using it to calculate the asked probabilities. First, let's figure out the PMF. Let's list down the values of x and then their corresponding probabilities. X can contain values 1, 2, 3, 4, and 5. When x is 1, the probability is 1 plus 2 over 25, which is 3 over 25. When x is 2, you have 2 plus 2 over 25, which is 4 over 25. When x is 3, 3 plus 2 is 5 over 25. When x is 4, you have 6 over 25. When x is 5, it will be 7 over 25. You can see that all these probabilities are less than 1 and greater than 0. So they are correct probability values. Not exceeding 1, not negative values. And then if you add these px's together, what will happen? 4 plus 3 is 7, plus 5 is 12. 12 plus 6, 18. 18 plus 7, 25. So you get 25 over 25, which is 1. So all two conditions are satisfied. Therefore, this is a valid PMF. Okay. Now let's see how we can calculate these asked probabilities. The first one is the probability that the x can contain values from 2 to 4, including 2 and 4. You can see the equal sign, less than or equal, less than or equal. So that will be 2, 4, 5, right? Including 2 and 4. So you have to add these probabilities together, which will be the probability at 2, probability at 3, plus probability at 4, which will be 4 plus 5 plus 6, which is 15 over 25. Okay, the next one is probability of x less than 2. So the less than 2, 2 is not contained. Okay, so you see only the less than. So it will be only when x is 1. So that probability is just P1, which is 3 over 25. You should see the difference between the equal, the less than or equal, and the less than. So if this contains the equal sign, you have to add px and px equals 1 and px equals 2, both of them. But here it is just the less than, so 2 is not included. Then we have the third one, px greater than or equal to 2. Greater than or equal. So these probabilities will be 2 is included. We have the equal sign. 3, 4, and 5. So you have to add up 4, 5, 6, and 7. Okay. So which will add up to 22 over 25. Or you can do this in another way. Since this is the complement of P1, right? This is same as the complement of P1. Because 1 is the only value which is not inside this set. 2, 3, 4, 5. So the only remaining is P1. So this is the complement of P1. So you can do 1 minus P1. 1 minus 3 over 25. So you can get the same answer. So sometimes it is easy to use the complement when you do calculations. Okay. Now let's look at a few other theorems related to the cumulative density function. The value capital Fx of the distribution function of a discrete random variable x satisfy the following conditions. The capital F at the negative infinity equals 0 and capital F at the positive infinity equals 1. We actually saw that when we did the graphical representation of the CDF. So you can see that the Fx is 0 all the way up to negative infinity, and soon after it attains 1, it will remain there up to the positive infinity. That is the first condition. The second one, if A is less than B, then capital Fa is always less than capital Fb for any real number AB. Okay, if we go back to the CDF of the previous example, you can see that always the capital Fx is increasing. This is increasing, see? So when you have two values, let's say 3 and 5, 3 is less than 5. So the capital F at 3 is also less than capital F at 5, because this is a strictly increasing function. In Theorem 3.3, we look at a way to calculate probabilities using the CDF. If the range of a random variable x consists of values x1 up to xn1, then the probability at x1 is same as the CDF of x1, okay, which means at the very first row you see the px and fx, they are the same. Okay, so that is the initial point. So for x1, that is the first element, you see px and fx, they are the same, 0.2. And then if you want to calculate pxi, that will be the CDF at xi subtract the CDF at the one above it, that is I minus 1. Okay, what is that? Say for example, if you need P5, you can find it by capital F at 5 subtracting capital F at 1 above it, which is 4. So let's see whether we can get that. Capital F at 5 is 0.9. If you subtract capital F at 0.4, which is 0.74, you get 0.16. And that is exactly P5. So it is easy to do calculations when you have the CDF. Okay. In example 3.4, you see a CDF of a certain random variable. Now this is the CDF. This is the proper way to write the CDF. Even for a discrete case, you see that from negative infinity up to whatever the first value you have in your sample space, the capital Fx is 0. Then at 0, you attain 1 over 16, and 1 over 16 will be there up to 1, and at 1, you attain 5 over 16, and so on. So if you draw the step function for this random variable x, here's x, and the CDF x, this is the capital X actually, 0, 1, 2, 3, up to 4 only, okay. So from negative infinity up to 1, you have 0. And at 1, it jumped up to 1 over 16. And it will remain up to should be 0. Hold on. Let's do it again. So, okay. So negative infinity up to 0, capital Fx is 0. Okay, this one. And at 0, it jumped up to 1 over 16 and remained there up to 1. At 1, it jumped up to 5 over 16 and remained there up to 2. At 2, it will attain 11 over 16 and remain there. At 3, it attains 15 over 16 and remain there. And at 4, it attains the total probability 1 and it will continue up to positive infinity. Here's the step function of this CDF. Now for this one, you have to find the PMF. How do we get the PMF out of the CDF? Okay, this is very simple. What you have to do is subtract the one above it. At x1, when x is 0, px and fx are same. Okay, so that will be 1 over 16. And at 1, you have 5 over 16 minus 1 over 16, which is 4 over 16. Then 11 over 16 minus 5 over 16, the one above it. You end up with 6 over 16. Then at 3, 15 minus 11 is again 4 over 16. And 1 is 16 over 16. So 16 minus 15 is 1 over 16. So what you do is you subtract always the CDF at x from the one above it. So you end up with these values for your PMF. Again, if you add them together, 1 and 4 is 5 and 6, 11. 11 plus 4, 15 plus 1, 16. So you get the total probability 16 over 16. So you have the CDF and the corresponding PDF. Okay, so we found the PMF. That's the first part. Now let's try to find probabilities. When you have both the CDF and the PMF, you can easily find these probabilities using either of them. So let's see how we can find x equals 2 using the PMF. Very easy. So here's x, here's the px, which is 6 over 16. If you use the CDF to find the px2, you use capital F at 2, subtract capital F at 1. Okay. So which will be 11 over 16 over 5 over 16. So you get 6 over 16. So you can use either the PMF or the CDF. So what about Px greater than or equal to 3? So that will be 3 and 4 together. So if you add P3 and P4, you get 4 plus 1, which is 5 over 16. Then the last one, you need probability x is in between 2 and 4. So that will be P2, P3 and P4. If you add them together, you get 6 plus 4, 10 plus 1, 11 over 16. Or if you want, you can use the CDF. This will be capital F at 4. Subtract, you need 2, so you have to go up to 1. Okay? Because you need 2, 3 and 4. Okay, so you have everything up to 4. You need 2, so you have to subtract everything above 1, that means 1 and 0. So the probability up to 1, that is F1, you have to subtract. If you do that, you'll end up with capital F at 4 is 1, that is the total probability, or 16 over 16. Capital F at 1 is 4 over 16. So 16 4 over 16 and 5 over 16 actually, which is the 5 over 16. Okay, so this is 5 over 16. 16 minus 5, you get 11 over 16. So it's the same answer. So either you use the PMF or the CDF. So you have to be careful when you have the equal sign, you do not subtract F2. If you subtract F2, you miss the probability assigned for 2. So you have to keep it. So you have to get rid of everything above it. So 0 and 1, which is the cumulative up to 1. So capital F 1. Okay. So that is how you calculate the PMF, the CDF, and the probabilities assigned to each of x when x are, or when x is a discrete random variable. Now the next section is the continuous random variables. So the third section, we look at again how to get the probability distribution and the cumulative density functions, how to represent them graphically, and calculate probabilities when you have continuous random variables. Now you know a continuous random variable is a variable that can contain all the values within a given interval. So the fractions, decimals, everything can be included. As an example, temperature in Celsius. If we draw a probability for a continuous random variable, it will be a smooth function, fx, and the probability assigned to fx will be all the values under this function fx, so we call it the total area under the curve. If you find the total area under this curve, that will give you the total probability 1. That is if fx is a probability distribution for a continuous random variable x. In order to find the total area under the curve, what we have to do is to integrate this function fx from its starting point to the end point. So the limits will be a to b. If you integrate the function fx over its limits a to b, you will get the total probability 1. That is the total area under the curve. If you need the probability at a point for a continuous random variable, the probability at a certain point is 0 because this is the point probability. If you integrate from c to c, you end up with 0. This is something you have to be very careful compared to discrete case and the continuous case. In continuous random variables, you can have point probabilities. We calculated px equals 2. See the point probability. But when it comes to continuous case, the point probability, the p at c, that is going to be 0. Let's define the probability distribution function for a continuous random variable. We denote it as PDF. For the discrete distributions or discrete random variables, we have the PMF, probability mass function. When it comes to continuous case, we use PDF for probability density function. It is the same thing but defined for two types of random variables. For discrete, we call PMF. For continuous, we call PDF. So here's the definition. A function with values fx defined over set of all real numbers is called a PDF of a continuous random variable x if and only if they satisfy these two conditions. The first condition is the probability from a to b, you can calculate it with this integration fx from a to b, and the point probability is 0, it cannot be found. Okay, so we call it a probability density function. And here's the important thing that relates to the point probability. If you find the probability from a to b including a and b, or without including a, or without including b, or without including both a and b, still they are the same. The reason is the point probability is 0. Again, you have to be very careful. This is not true for discrete cases. When it is a PMF for a discrete random variable x, these four probabilities are different. But when it comes to continuous random variables, since the point probability is 0, including A or including B in your interval does not matter, because at P equals A or at Px equals B, they are 0. They are the point probabilities. So whether you include it or not does not matter. All of these probabilities are same. But in the discrete case, that is a different. Okay. A function can serve as a probability density or PDF for a continuous random variable if it satisfies the two conditions related to the PMF. You have the same thing. Fx should be greater than 0. And if you integrate over the whole support of x, or from negative infinity up to plus infinity, that is the total area under the curve, it should be 1. That is the total probability. Okay. So for a given function fx, if you want to check whether it is a valid PDF, you have to check these two conditions. Okay, let's look at an example. Now look at how this fx is written. You see the function fx. The value of fx when x is from 0 to 2, that will be k times x square, and all the other places it is 0. So this is called the support of our random variable x. OW is a short form for otherwise. Okay, whenever you see OW, or sometimes we use O/W, that is for otherwise. Now let's see whether this fx is a proper or valid PDF. And then let's find the probabilities given in part A and part B. Okay. The first thing you have to do is to find the value k such that fx is a valid PDF. So how do you do that? We know that according to the second condition in Theorem 3.5, if you integrate your fx from negative infinity up to plus infinity, it should be 1. Which means if you take this fx and integrate from negative infinity up to plus infinity, it should be 1. We know that the support of x is from 0 to 2. Therefore, from negative infinity up to 0, and then we have 0 up to 2, and then we have 2 up to plus infinity. This should be 1, but it says from 0 to 2 you have this function kx square dx, and all the other places it is 0, so this will be 0, the other side is also 0. So therefore, when you have to do integrations for PDFs, you can straight away write the integration over the given limit or the support, because all the other places it will be 0. Okay, so you can omit writing the negative infinity up to plus infinity all the time and start away straight with the given support. This should be 1. Okay, now let's try to find the value of k. Since k is a constant, let's take it outside the integration. You have to integrate from 0 to 2 x square dx. This should be 1. X square, the antiderivative will be x3 over 3. Evaluate from 0 to 2. This is 1. So we get k over 3. When x is 2, 2 to the power 3 is 8. When x is 0, 0 to the power 3 is 0. This is 1 equals 1. So you have k times 8 over 3 equals 1. So k will be 3 over 8. So here's the value of k so that fx is a valid PDF. So we apply this. The integration from 0 to 2 equals 1. That is the information about the valid PDF. The total probability or the area under the curve should be 1 over the support. So 0 to 2, this function should be 1. Using that equation, we can calculate the value of k. So which will be 3 over 8. Now you can write your fx using the value of k. So our fx is x is 3 over 8 x square over the support x from 0 to 2 and 0 otherwise. Okay, so this is how you write a PDF in a correct way. Right. Now let's try to find the probabilities. The first one, you have to find the probability x is from 0 to 1. How do you find that? Now you know the function fx. You have to integrate it from 0 to 1. So 0 to 1, 3 over 8 x square dx. Let's take the constant outside. And x square is x3 over 3, the antiderivative from 0 to 1. And this 3 and this 3 will cancel out, so we don't have it anymore. We have 1 over 8. X at 1 to the power 3 is 1 and 0. So the probability from x0 to 1 is 1 over 8. After you calculate probabilities, always check that it is a correct probability value. Your probability value cannot exceed 1 or it cannot be negative. So if you end up a value for a probability which is greater than 1 or a negative value, which means you have done your calculation wrongly at some place. So you have to make sure you get a proper value for your probability. Part B, you have to find x from 1 to 2. Okay. Probability x from 1 to 2. Now remember, if you write this as 1, 2, that is also the same thing. Okay. So integrate from 1 to 2, 3 over 8 x square dx. This is the constant. You have x to the power 3 over 3. Evaluate from 1 to 2. Again, 3 will cancel out. When x is 2, 2 to the power 3 is 8. When it's 1, 1 to the power 3 is 1. So you end up with 7 over 8. Okay, so you have 0 to 1, 1 over 8, 1 to 2, 7 over 8, altogether 1 to 2, you have 8 over 8, the total probability 1. So this is how you calculate probabilities, and if there is a constant, you can find it using the valid PDF property. Or if you have the exact function given here, if you want to check whether this is a valid PDF, you can do the integration over the support and check whether you can end up with the total probability 1. And then you can calculate corresponding probabilities. I hope this is clear to all of you. Okay, here's another one. Find the value of k such that fx is a valid PDF. You see the exponential function here. Okay, let's try to find the answer. The support is x greater than 0, which means the support of x is from 0 up to plus infinity. K times e to the negative 3x dx. This should be 1 if it is a valid PDF. So let's solve this one and see what is the value of k. Again, let's take k outside. It is a constant. 0 to infinity e to the negative 3x dx. So this is e to the negative 3x divided by negative 3. If you can remember, finding the antiderivative of the exponents. Evaluate from 0 to infinity. This should be 1. Okay, so let's write negative 3 here. Evaluate e to the negative 3x from 0 to infinity. When x goes to infinity, you have e to the negative infinity, which is 1 over infinity, 0. Subtract. When x is 0, you have e to the 0. Any value to the power 0 is 1. You have 1 minus 1. So you have negative 1 here and negative 1 here will cancel out. And we'll end up with k over 3 equals 1, which means k is 3. Okay? Therefore, we can write our function fx 3 times e to the negative 3x, x greater than 0, 0, otherwise. Okay, so OW for otherwise. Now we have the value of k. Now let's try to calculate the given probabilities. You need the probability from 0.5 up to 1. So let's integrate 0.5 up to 1, 3 e to the negative 3x dx. Okay, so 3 is the constant, e to the negative 3x, antiderivative negative 3, evaluate from 0.5 up to 1. So this 3 will cancel out, but you have negative 1 in front. Evaluate e to the negative 3x at x is 1, you get e to the negative 3 minus e to the negative 3 times 0.5. Okay, when you have the negative 1 in front, you can write e to the 3 times 0.5 is negative 1.5 minus e to the negative 3. Okay, by multiplying this by negative 1, you end up with this answer. So if you want, you can use a calculator and find the exact value of this answer. So I leave that to you. Let's do the next one, part B. We have to find the probability from 1 to 5. X from 1 to 5. So let's integrate our function from 1 to 5. 3 times e to the negative 3x dx. 3 is the constant. E to the negative 3x, the antiderivative. Evaluate from 1 to 5. Again, you have 3 cancels out. Negative 1 outside is negative 1. E to the negative 3x evaluate at 5 is e to the 3 times 5, e to the negative 15. When x is 1, e to the negative 3. So you have the negative 1 outside. So multiply by negative 1, you end up with e to the negative 3 minus e to the negative 15. So again, if you use a calculator, you can find the exact probability. Okay? Right. Now we have to find the CDF. or the cumulative distribution function for a continuous random variable also. We have already learned how to find the CDF for a discrete random variable. Now we will do the same for a continuous random variable. So for a continuous random variable x, capital X, the value of its PDF at, let's say, t, the function given by capital Fx, again, that is the CDF, is the probability x is less than or equal to x. Instead of the summation, now you have the integration. So if you integrate from negative infinity up to whatever this x, you get the CDF at x. So for a discrete case, the CDF will be calculated using the summation. For a continuous random variable, the CDF will be calculated using the integration. Okay. And very similar to the discrete case, you have the two properties of the CDF. When the CDF is at negative infinity, the value is 0. For positive infinity, it is the total probability 1. And for any two real numbers, a and b, where a is less than or equal to b, you can find that the capital F at a is also less than capital F at b, because this is a increasing function. So if you draw the graphical representation of the CDF for a continuous random variable. So suppose the support is from A to B, is the total probability 1. So you have 0, and then it will go and attain 1 at B, and it will remain there up to negative infinity. Positive infinity. So here's the CDF. It is increasing, always adding values, and at the end of the support, it attains the total probability 1, and then it will remain at 1 all the way up to positive infinity. Okay. Let's look at another example. So I have given the PDF of capital X, or the random variable x. It is 3 over 8 x squared. So we already used this example actually. Let's try to find the CDF of this PDF. Okay, so we use the definition, which is the probability x less than or equal x. So you have to integrate your function fx from negative infinity up to x. Our function is 3 over 8 x squared. The support start from 0. So negative infinity up to 0, everything is 0. So you can omit writing it. So integrate from 0 up to any x. X can be any value. Okay, so we have 3 over 8, the constant. Antiderivative of x squared is x3 over 3. Evaluate it from 0 to x. So we get x to the power 3 over 8 from 0 to x. So when x is x, it's simply x to the 3. When x is 0, we have 0. So the CDF is simply x to the power 3 over 8. Now this is not the final answer. You have to make sure you write it in the proper way. So this is how you write a CDF in the proper way. The support starts at 0. For all the x's less than 0, the value is 0. Then x from 0 to 2, the CDF will be x to the power 3 over 8, and after 2, it attains total probability 1. So this is how you should write your CDF. When you have to find the CDF for a given PDF, do not stop your answer from here. Okay, so the final answer should be the proper way of writing capital Fx. Okay, so you have the capital Fx within the support, and also up to the negative infinity it is 0, positive infinity, everything above 2 up to positive infinity, the total probability 1. So all these information should be in your final answer, capital Fx. Okay, right. So here's the second example we did again. So you have to find the CDF and some probabilities. Since you already know how to calculate probabilities for this example, I'll omit parts B and C, but let's see what will be the capital Fx. Okay. How do you find the CDF? You have to integrate from negative infinity up to x, fx dx. Okay. And our support starts from 0. So it is 0 up to any x, 3 e to the negative 3x dx. Okay. So here's the constant. The antiderivative, evaluate from 0 to x. We have negative 1 outside. E to the negative 3x evaluate at x is still e to the negative 3x. When x is 0, e to the 0 is 1. Multiply by 1, negative 1, you end up with 1 minus e to the negative 3x. Here's the CDF of fx. Now, you have to write it in the proper way. Zero when x is less than 0. Since x contains values all the way up to plus infinity, in this case, you simply write this one, 1 minus e to the negative 3x. Yes, the CDF of x. Okay. Now, in this one, I can show you an easier way to do calculations for the probability px less than 0.5. Now, there are two ways to do this. If you do not have the CDF, you can do the integration x less than 0.5. It's from the lower limit up to 0.5 fx dx. So this is the usual way you can find the probability. But if you have the CDF, you can easily find this because this is the definition of the CDF. So this is exactly capital F at 0.5. Right? This is same as capital F or the CDF at 0.5. Since you already have the function fx, if you want to find f.5, what you have to do is you take your fx, which is 1 minus e to the negative 3x. Instead of x, you write the value you want, which is 0.5. So rather than doing the integration again and doing this calculation, since you have already done the integration up to any x, right? You have already done the integration up to any x. So when you have capital F at 0.5, simply substitute 0.5 to your capital Fx. So you get the answer. This will be 1 minus e to the negative 1.5. Right? So if you do the integration, you'll get the same answer. Okay. What about the part C? That is also easy if you have the CDF. So you need 1 up to 5. Okay, so one method is you can integrate the whole function from 1 to 5. Right? Or what you can do is this is f5 subtract f1. Right? Since this is the continuous case, the equal sign does not matter. So it will be simply capital F at 5 subtract capital F at 1. So you know the capital Fx. So when it is 0.5, you get 1 minus e to the negative 3 times 5 subtract 1 minus e to the negative 3 times when x is 1. Right, so what do you get? 1 minus e to the negative 15 minus 1 minus e to the negative 3. Negative 1 plus e to the negative 3 after removing the parentheses. So plus 1 and negative 1 will cancel out. You get e to the negative 3 minus e to the negative 15. Okay. So if you want to double check, integrate this fx from 1 to 5 and see whether you can end up with the same answer. You should. Okay. Here's the next theorem, 3.6. If simple fx and capital Fx are the values of the PDF and the CDF, respectively, if you want to find the probability x from A to B, you can do that with capital FB minus capital FA. So this is what we did in part C, right? Our A is 1 and B is 5. So we have already used this theorem in answering question number example 3.7 part C. And also, if you want to find simple fx from the capital Fx, that is the PDF from the CDF, you can do that easily. Because the reverse of the integration is the derivative. If you take the CDF and get the first derivative, you can get the PDF. You can do that only for the continuous random variables, okay, where you have the integrations and the derivatives. So here's the example. You have to find the PDF of this given CDF. You can see the support of x is from 0 to 1. Okay. So you have the capital Fx given in this expression. We want to find PDF, which is Fx. That will be the first derivative of the given function. Okay. So let's take the constant out. We take the derivative of x to the power 3 over 3 and the derivative of x square over 2. So this will be 3 to the x square over 3. This is 2x over 2. Values cancel out. You'll end up with 6 over 5 x square plus x. Okay, so here's the PDF of the random variable x by taking the first derivative respect to x. Now you have to write it in the proper way, otherwise the answer is not complete. The support is from 0 to 1. Zero otherwise. If you want to check whether this is a legitimate PDF, you can check it, integrate over the support and see whether you can get 1. Okay, let's try it. Integrate from 0 to 1. Six over 5 is the constant. X square, x 3 over 3. Okay. So let's try to get the common denominator. This is 2 times x to the 3 plus 3x squared. Evaluate from 0 to 1. So you have 6 is gone now. 1 over 5. X is 1 and 0. It's just 1, so it is 2. And x is again 1 and 0. 1 minus 0, again 1, so it's just 3. So you have 5 over 5, 1. So this is a correct PDF. Okay, so this is just checking whether you have done your integration correctly or the derivative correctly. Okay. Here's the final example. The completion time x for a certain task has the following PDF. Now in this one you can see the function fx is a piecewise function. From 0 to 1 it behaves as x squared, the quadratic function. From 1 to 7 over 3, another function, a linear function, and 0 otherwise. Using this PDF, let's try to answer these questions. The first one is fx is a valid PDF. So what you have to do is integrate your fx over the support and check whether this is a valid PDF. Now in this question, when you do that, you have a split support. So from 0 to 1, you have a certain fx, and from 1 to 7 over 3, the next one. Okay. So you have to do this integration for the two limits separately. Okay, so let's try to do that. From 0 to 1, it is x squared. From 1 to 7 over 3, it is this given expression. Okay, so this will be x to the power 3 over 3, 0 to 1, plus 7 over 4x. You will get from 1 to 7 over 3, minus 3 over 4 is a constant, x squared over 2, you will get from 1 to 7 over 3. Okay, x evaluate from 1 to 0, it will be 1 over this 3, have 7 over 4, x at 7 over 3 minus 1, evaluating 7 over 3 and 1 at x. Then you have 3 over 4 times 2 is 8. X square evaluate at 7 over 3, 49 over 9 minus 1. So you have to do this calculation, simplify it and see if you can get the total probability 1. Let's try it. Okay, what do we have here? Let's do the cancellation. It's minus and minus becomes plus 1 over. Now you don't have the cancellation 3, so it is 3 over 8. Okay. Let's try to get the common factor. Let's 24, 8, 49 times 2 is 98, 6 times 7 is 42, minus 49 plus 9. Okay, so the positive values, we get 98 plus 8, 106 plus 9, 115 minus 42 plus 49, 91. So 115 minus 91, you get 24. So 24 over 24 is 1. So this is a correct PDF. Okay, so this is a valid PDF. Okay. Now you have to find the probability x is less than 1.5. How do you do that? Okay, before that, part B, x less than 0.5. Less than 0.5. Okay, so I have to be careful about the support. 0.5 is within the first support, 0 to 1. So you have to use only this function x squared. Okay, because 0.5 is within this interval 0 to 1. So when you do the integration, so this will be, the lower limit is 0 up to 0.5. The corresponding function is x squared. Okay, so you can find that probability. Now the next one is x less than 1.5. So I do not do the integration, you can find it. I'll show you how to get it only. Okay. So when x is less than 1.5, 1.5 is here in the second interval, right? So 1 up to 1.5 you have to use this second function, and for the other support, the rest of the support, you have to use the first function. Okay. So when x is less than 1.5, this means x is from 0 to 1 and from 1 to 1.5. Okay. So from 0 to 1 you have to use x squared dx, and from 1 to 1.5 you have to use the next one. Because this is the piecewise function, you have to use the corresponding function at the correct limit. Okay, so 7 over 4 minus 3x over 4. Okay, so this is how you find the probability when you have piecewise functions. So you have to use the correct function in the proper places. Okay. Part D, you have to find the probability from 1 to 2. Okay. So 1 is there. 2 is also within that interval. So you can use only the second function to answer part D. Okay. So for part D, (1 to 2) you use the function 7 over 4 minus 3x over 4. Okay. So make sure you know what the exact value. It's 7 over 3. What is it? So it's 3.333 and something. Okay, so this 7 over 3 is greater than 3. Okay. Then you need to find the probability x greater than 4 over 3. Okay, so 4 over 3, what is that value? It's 1.3 and so on. So that is within the second part, second piece. So you have used that function f(x) to answer part E, x greater than 4 over 3. So I have to integrate 4 over 3 all the way up to 7 over 3. So that is the limit, upper limit. You integrate up to plus infinity, but 7 over 3 up to plus infinity, it's 0. So you go up to the upper limit of the support. So 4 over 3 up to 7 over 3, we integrate this function 7 over 4 minus 3x over 4. Now you can get the probability. Okay, I hope this is clear for all of you. I am not doing the calculations. You can try them by yourself. And each and every time you calculate a probability, check whether it is a valid value for probability. It cannot be negative. It cannot exceed 1. If you get any value greater than 1 or negative value for a probability, double check your calculation because you have done a mistake somewhere. Okay, so that is the end of chapter 3. So in chapter 3 we learned about the probability density functions, probability mass functions, cumulative density functions, and how to calculate probabilities when you have a random variable x, which is a discrete one or a continuous one. So if x is discrete, the way you represent the total probability 1 distributed among all possible values of x is the PMF. When x is continuous, you have the corresponding distributive function, we name it as the PDF. PMF we denote it as PX, PDF we denote them as FX. These are just the notations and names. The same thing defined for a discrete or continuous. And for both cases, you have the CDF, which we denote as capital Fx. For the discrete case, we find the CDF using the summation of Px all the way from negative infinity up to a certain x. For the continuous case, we integrate Fx all the way from negative infinity up to the whatever the value x. And then you can calculate probabilities either using the PMF or the CDF or PDF or the CDF. So this is the end of chapter 3, and in chapter 4 we'll look at how to calculate averages using PMF and PDF.